I want to also thank INQUA and everybody here for inviting me. I'm going to talk today about a lake in Guatemala called Lake Isabel. And this is sort of work that I've been doing together with Jonathan Oberst-Farner and all of our colleagues. You can see there's a fairly massive list of authors. Those are just the people who are sort of responsible for most of what I'm talking about today. And so this isn't something that's just my own work, but rather a collaboration between a bunch of people. But primarily the diatom work is all mine. So we're going to talk today about this and then maybe a little bit about some of the other lakes in Guatemala that we're looking at with related work. This is partly stuff that we published in a paper in 2021, a little bit about the Lake Isabel system, and then some stuff that's basically going to come out relatively soon in, I think, Science of the Total Environment, and a new paper that's going to come out in Geology that looks at some of the other stuff that I'll talk about today. So make this advance. First thing I want to do is give you a little bit of background about diatoms if you're not familiar with them. Typically, we cannot see them in hand samples unless they become very massive. And so in very few instances, diatoms have actually managed to get common names. This is an example of a diatom that is known as rock snot, a very colorful name, but you can tell from the image here that where it gets its name from. So they create these massive amounts of material, but normally diatoms are basically invisible to us. And while they might look hideous in this sort of hand sample format, when we start to look at them in the light microscope or in the scanning electron microscope especially, they have very beautiful forms. And so they're sort of a charismatic group of microscopic algae. And diatoms are characterized by being unicellular and having a siliceous skeleton that has two valves. So two halves that basically normally are articulated. When the diatom dies, they sometimes disarticulate. And there's a wide range of different types of habitats that diatoms can live in. They can live either as solitary, sort of free-floating, or sometimes crawling organisms, or they can live in colonies. One of the things that I wanted to emphasize is that diatoms are found in basically all aquatic and subaquatic environments that you can imagine, and I will briefly go across some of these environments and give you some examples. But one of the reasons that we use them for palaeolimnology so effectively is that they reproduce very rapidly. They have very short lifespans, somewhere in the range of weeks to months in terms of how long they live. And they're highly sensitive to environmental changes. So, when we see a group of diatoms, they usually indicate something to us about a very specific type of environment that they occupy. And so as a result, they are excellent bioindicators for us, especially since they leave a fossil behind. So the siliceous part of their skeleton is actually left behind in the sediments. And so as a result, we can utilize that in the fossil record to basically reconstruct all kinds of environments that the living diatoms might have been in occupying when they were alive. So to expand on that, I wanted to say that diatoms are extremely diverse. So one of the things that we know about them is that there are more than 200 extant genera. And probably that number is growing every day as we see more and more diversity becoming clearer to us. There are some estimates currently that there may be as many as 2 million diatom species. I think the known published number is closer to sort of 30,000, but there's a lot of unknown species that are out there, and that kind of makes my work a sort of interesting combination of doing ecological reconstructions and also running into an endless number of new diatoms, especially when we work in environments that are basically underexplored. And for people who just wanted to have some background about why diatoms are so important, they're basically the base of the food pyramid in pretty much all aquatic ecosystems. And so they are a fundamental food source for basically fish and zooplankton and snails and everything up the food chain. And unlike many other algae, most diatoms do not create, especially in freshwater, do not create toxic chemicals that prohibit organisms from eating them or create problems for their health. And so they're highly productive. And another thing is obviously that they're photosynthetic, and so they are really important oxygen producers. The estimates for how much oxygen diatoms produce is somewhere in the range of 20% to 50% of the oxygen that you breathe. So that's a substantial amount, and they're usually just not carefully promoted that way when we think about like diatoms and their importance in the world. As I mentioned, they're found in all kinds of different habitats. I'm just very briefly going to give you some examples. This is diatoms that were found living in Mono Lake. Mono Lake is, of course, classically and historically has had pH values that are very high. So in the 10 to 11 pH range, and diatoms have no problem living in these conditions. So there's a specific group of diatoms that we find living in basically hyperalkaline systems. And so just as a character that we could potentially use, if we saw a lake that shifted to being much more alkaline, we might expect to see a change in the assemblage associated with that pattern. This is the other extreme of that. So this is a diatom that we observed in a small creek here in Terre Haute, Indiana, which has a pH that typically ranges somewhere down to near zero, so extremely acidic, up to somewhere around 4 or 5. And diatoms have of specific types have no problem living in this kind of condition. So you can see they range across the entire pH spectrum, and that makes them a very valuable indicator for us when we're looking at pH in lake systems. We're trying to figure out like what the pH of the environment is. There are diatoms that have been collected from thermal hot springs. So this is basically at the upper limit of where photosynthesis can occur, which is roughly around 75 degrees. And so at 75 degrees Celsius, the water is basically pretty close to boiling, and there are diatoms that have been found living and thriving in some of these communities that are up to 70 degrees Celsius. So very warm conditions are not a limit. Very cold conditions are also not a limit. So these are diatoms that have been frozen into the bottom of sea ice. These are actually really interesting extremophiles because not only are they living in extremely cold conditions, but also this is sea ice. So in order for the sea ice to actually turn into ice from water, the salts get purged out of it. And so this is not only a hypersalining environment, but also a extremely cold environment. And so you can see they go across the entire spectrum of very warm to the coldest places that you can imagine. And these are diatoms that thrive in those conditions. That brown part of the ice that you can see is basically masses of diatoms that are growing in the bottom of sea ice. So, and living, not just like frozen in it, but actually actively living in those environments. If you're wondering where else they might live, this is an example of diatoms that have been collected from mosses and tree barks. So these are not usually what we think of as lake habitats, but they're definitely subaquatic habitats where diatoms have no problem thriving. And so in conditions that basically are wet and dry and exposed to the open air, there are specific groups of diatoms that basically have been found in these types of environments as well. Even in places where you wouldn't think diatoms could be found, these are tank bromeliads. These are basically jungle plants that get rainwater that fills up a container that's created by the leaves of the plant. So if you're thinking about what could possibly be the lowest nutrient environment on planet Earth, it's just basically rainwater that collects in the plants. And people have found diatoms living in these little pools of water that basically have almost unmeasurable amounts of nutrients in them. So again, on every extreme environment that we can think of, diatoms have not only grown, but thrived in those conditions. They also live in places like soils, for example. There's a lot of recent work looking at the soil distribution of diatoms, which is actually kind of fascinating. But they're found in all kinds of soil environments only up near the surface. And so when it rains very hard, and I go out and sample some of the water from my driveway, these are the diatoms that actually show up in that material. So we know that they're living in sort of soil environments around the world as well. And these are typically not the environments that we would see, diatoms we would see living in lake systems, but rather have very uniquely adapted conditions to these. And not to be left out, humans have actually modified a lot of the planet, and we find diatoms living on man-made structures all the time, the sides of buildings, on sidewalks. And this is an example of also some that are recovered from wet cave walls, the surfaces of man-made structures in basically any environment where there's a little bit of water and some sunlight. You can find diatoms, and I would actually argue that some recent work that Andy Alverson and I have been working on, there are diatoms that have been growing for months without sunlight. So even in dark environments, you can find diatoms living in settings like that, where they switch between being photosynthesizers and being capable of heterotrophy. So all unique. What I'm trying to get at is that diatoms are basically found in all kinds of different environments. And as a result, when you see water anywhere on planet Earth, you should expect that there's probably some diatoms living in that water, or even if it's just moderately wet environment. So they're extremely common. They have excellent preservation potential. So across all of these, basically, their skeletons will be preserved, except for when we get into very high pH ranges, where I'll talk about a little bit, the silica starts to dissolve. They have a very small amount of sediment that's required. So in the amount that's basically the size of a pea, you'll find millions of diatom valves. And so we don't need a lot of sediment in order to analyze them, which makes them excellent indicators for us for lake sediments. All of my colleagues are very happy to find that I don't really require much sample, so they can use the rest of it for whatever else they're doing. They grow very rapidly. We know that they evolve rapidly, and we have many species that are thought to be cosmopolitan species that we find basically across the planet. They have very short lifespans, and they can colonize environments very quickly. And what I'm trying to showcase for you is that basically they are an ideal biological indicator that we could use from lake sediments to reconstruct basically any kind of environment. There are some taphonomic biases associated with diatoms. The primary one that creates the most problem is that when the pH becomes very high, they start to dissolve. And this is some work that David Rives did, talking about how we could actually use that information where the diatoms start to dissolve. It often leaves us with no diatoms preserved, or very poorly preserved diatoms, but it tells us something about that actual environment when we see it, because if there are no diatoms present, we can make some assumptions that diatoms were probably living in that environment and then basically got dissolved out. So they indicate to us that the pH was probably very high in those conditions. And it can actually improve our interpretations if we think about the absence of diatoms representing some very specific type of environment that's giving us some information, even though the diatoms aren't present in it. Okay, so diatoms have this wide range of different environments. They also have a bunch of different ways that they can live. The most common ways that I usually see them are these three main groups. The euplankton, those are things that are basically floating in the water column all the time. And they try to basically stay in the sunlit zone of lake systems. And so what that means is they're often trying to slow down their settling velocity, how fast they fall through the water column, so that they can remain in the sunlight zone. And the lake mixing, the large-scale convective mixing that pulls diatoms back to the surface in any kind of lake system, usually results in these diatoms being suspended in the water. But sometimes they'll actually basically hang out at vertical boundaries where there's density gradients between the upper waters and the lower waters of lake systems. And so they have a bunch of different strategies for basically remaining afloat. Sometimes they create these sort of like parachute-like structures that sort of stick out from the valves. But basically what they want to do is remain in the sunlight. And so they want to either make themselves as light as possible or find some way to baffle their descent. There are other types of diatoms that we call meroplankton, or I call meroplankton. They have a staged planktic lifestyle, so part of the time they want to be in the water column when the water's mixing and there's a lot of nutrients present, and the rest of the time they don't really want to be there because the water doesn't have enough nutrients for those particular groups. And so they create these large, heavy valves that form chains. You can see some examples of the chains in these images. Here's a long chain that just happened to be preserved in the light microscope, a sort of unique feature, but typically they disaggregate when they're found in the fossil record. So this is kind of a rare setting. But the heavier valves and the colonies that they form in mean that they sink a lot faster, and they have to basically develop a lifestyle that allows them to basically insist so that they can survive during periods of darkness when they're at the bottom. Sometimes they use this as part of their strategy. They'll form sort of sticky clumps, and when they go to the bottom, they take all the other diatoms with them and carry them down into the hypolimnion. And we've been able to, through a bunch of different studies, been able to find that groups like Algae, for example, can actually detect how much silica is in the water around them. And they can change the length of their valves basically to respond to the amount of silica that's in the water. So if the nutrients are low, they basically will create heavy, long chains that fall through the water column. And if the nutrients are abundant, they'll rapidly reproduce. And then so basically they can make adjustments to the length of the chain that they're creating, and they often do this in response to the environments that are around them. The last group I wanted to talk about is just benthic diatoms, some more common types of diatoms growing on rocks and mud, and some of them are free crawling organisms that basically can get around. So they live attached to plants, and sometimes they're zooplankton. And they're limited by basically being in the sunlit part of lake systems. So wherever the light penetrates to the bottom, the diatoms can live in those settings. They can reposition themselves. As I mentioned, they have a mechanism called a raphe that they use to basically crawl around. They don't move very fast, but they can basically reposition themselves into the light or out of drying conditions into more aquatic, rich environments. And because they're limited by sunlight and the combination of sunlight and substrate, they are required to basically live in shallow water unless they're attached to something that's swimming or floating. Basically, they're going to be found in shallow water. So we usually use them to give us some indication of changes in lake level. So this is an example from some of my PhD work. The normal conditions for the lake are deep water, and you get the things that are visible in the upper image, which are plankton. The things in the bottom part are euplankton, I should say. The things that are in the bottom part are benthic diatoms, but these were collected from a core at the exact same location. And so where the sediments are full of plankton, I know that that was deep water. Where the sediments are full of benthic diatoms, I know that that was shallow water. And it suggests that there's a big change in lake level associated with it, where we observe this. We've also used diatoms, as I mentioned, for all kinds of things, but lake level is probably the thing that's most dear to me with respect to how frequently we use them in palaeolimnology. Many people have also used them for reconstructing things like pH. The original reconstructions from diatoms were largely driven by studies that were looking at things like acid rain, but diatoms can be arranged in the order of increasing preference for different types of pH and basically give us a very good sense of acidity in the environment. They're used for indicators of salinity. So diatoms are very sensitive to salinity across the gradient from freshwater all the way into the marine realm. Diatoms are common in the ocean, they're common in lake environments, but typically things you find in lake environments are never found in the ocean, and things that you find in the ocean environments are never found or almost never found in freshwater environments. And so the most common marine genera don't even occur in freshwater systems and vice versa. So that at a much higher level, basically they're connected to these salinity gradients. And we often use this to basically reconstruct past salinity changes in lake systems using diatoms. This is an example of pH, light at the bottom, total phosphorus, and nitrogen, all examples of things that we can very easily arrange diatoms by their optima and then use these to reconstruct very specific values based on their preferred environments. Okay, so with that as a background, I'm going to talk a little bit today about Lake Isabel. And Lake Isabel is a lake in Guatemala. It's the largest lake in Guatemala, a natural lake in lake system. It's about 15 meters deep at its deepest point, and it is very close to sea level. So during normal conditions for the lake, it's about 1.5 meters above sea level, and the water from the lake basically during the wet season will be transported out the Dulce River into El Golfete, which is a small sort of like, it's almost like a wide part of a lake, but it's also considered to be a small lake on its own. And from there, it goes out into the Caribbean Sea. So this is the normal sort of flow during the wet period. The country of Guatemala receives a substantial amount of rainfall, typically between April and October or November, and something in the range of 2 to 3 meters of water fall on this area during that time. And that water basically keeps most of the seawater at bay. During the dry season, however, a lot of times what will happen is pulses of saline water will make their way up through the Antigua Bay into El Golfete, and in some cases all the way into Lake Isabel. So we do get these transitions where we see some salt water that basically makes its way a little bit into Lake Isabel. And this is actually the focus of my research that we're going to talk about today, which is looking at what happens to Lake Isabel under these conditions where either sea level rises or some combination of Lake Isabel's becomes dry and then sea level rises, and we get a pulse of seawater that comes into Lake Isabel. So in order to explore this, my colleague Jonathan Oberst-Farner and some of his colleagues collected a series of cores from Lake Isabel. I think this was in 2018. I started working on Lake Isabel in 2019 when I met John at a conference, and he was like, I need some help with some of these cores. We have diatoms in them, and convinced me that I should look at them. And so these are 5 cores that were collected from the Lake Isabel system, and these sediment records basically span from the current day all the way back to about the end of the Holocene. These are some dated sections from those cores. Cores 1, 2, 3, and 4 really haven't been studied very carefully, but core 5 has gotten a lot of attention. It's also the one that I was asked to analyze the diatoms for at low resolution. So we have a first blush of what's going on with the storyline here. The sediments themselves have an interesting characteristic. At the base of this diagram, you can see what it marks as a flooding surface. And that flooding surface is a change in the sedimentology between this sort of basically unlaminated section and then these finely laminated, probably varve-like deposits that occur above it. And our determination after studying this is that this is actually a flooding surface where the previous lake sediments are inundated with marine waters. And I'll explain how we came to that conclusion in a bit here. But this is the sort of overview of all those cores that were collected. This is just Lake Isabel's core 5, so one core from that sequence. And this is the one that's most carefully dated. The age depth model that we have is based on 10 radiocarbon dates. And here you can see the sort of boundary between the pink and the green is where that flooding surface is that we, between the pink and the white is the boundary here at the base that we, around 8,000 years ago, we see this transition. And then this boundary between the pink and the green is another one that I will talk about as we move forward. But the general model for what we see has been clearly defined by a bunch of different types of indicators. And one of the ways that we were able to basically connect all of the timing of the events of these things between the cores is by looking at magnetic susceptibility. So you can see there's a very sharp gradient between the base of the core and around 5,000 years ago. There's this huge transition in magnetic susceptibility and another peak in susceptibility around 2,000 years, followed by a progressive decline. And we've been able to use that magnetic susceptibility peak to find basically the same intervals across all 5 of those cores. You'll also note that there's a big change in the total organic carbon, and interestingly, a significant change that we see associated with the total sulfur in the core. So, and you can see the ratio of total sulfur to total organic carbon as well. All of them have these very distinct boundaries. The boundary at the base of the flooding surface, what we think is marine inundation, is part of the reason we believe that this is marine inundation is because we see a pulse of or an increase in the total sulfur in the system. And we think this is basically the lake being converted into euthynic conditions where the bottom waters become anoxic, and also a bunch of sulfur associated with sulfates in marine waters basically make their way into the lake system. And so we view this as the first of 2 marine incursion events. And then the lake basically sort of spends a long time in this condition where some of that seawater is present in the lake. The bottom waters become anoxic. When the bottom waters become anoxic, basically it causes a degradation in a lot of the iron-bearing minerals that are in the sediments, and they are no longer preserved. And then, so you can see the magnetic susceptibility drops off, and it also causes a lot of the organic carbon to be cannibalized and not preserved. And so we think this is a major transition in the lake's history. And then you can see these changes in magnetic susceptibility suggest there's another big pulse or transition basically around 2,000 years ago. When we look at this across all of the cores, the pink on this is not very clear, but there's a boundary at the base of this flooding surface that's down here, where you see the laminations start to occur. And then across all of the cores, you can also see this transition, the secondary transition in magnetic susceptibility associated with the lake converting back to normal conditions. And then a second pulse in here where the magnetic susceptibility drops and then returns to normal again. And so we can use these to basically find this correlation between them. The lower part is a sort of euthynic zone. The green bands are zones where there's a bunch of sulfates preserved in the core as well. And so we think that those are associated with this sort of transition back into normal lake conditions. And when we look at the diatom stratigraphy, so one of the reasons that Jonathan asked me to look at this core when we first started was to try to see what the diatom record could potentially tell us about this system. What we see is that at the very base of the core, there's a lot of benthic species. There's not a lot of plankton, so we know that there was a lot of shallow water conditions where the light was reaching the bottom where the core was collected or near where the core was collected. A lot of the diatoms that we see in that benthic interval are acidophilic species, things like Eunotia and Frastulia, which are known to be found in sort of like dystrophic conditions, wetland conditions. And so we think that most of the lake at this point was pretty shallow at the sort of transition into the record at the very base of our core. And they're freshwater diatoms. So we're seeing things that are basically found in the modern wetlands today that are adjacent to Lake Isabel, suggesting that the lake was just lower than normal. We don't have any plankton present, or really not much plankton present in the system, so it's probably shallow water near the site, suggesting that the lake was at a low stand. And this is followed by a transition very rapidly into planktonic species. And if we look at what those planktonic species are, they're dominantly Thalassiocyra. We also see a little bit of granulata, Algae granulata, and also not drawn on here, we occasionally see in some of the cores that we've looked at from the most recent stuff, Actinocyclus. So these are indication of elevated salinity and alkalinity, and also a rapid change in lake level. And so we associate this transition where it went from a shallow benthic dominated wetland-like setting into this sort of salty water as a flux of seawater that basically came into the bay, up into El Golfete, and pushed its way all the way into Lake Isabel. And this increase in in lake level that's dominated by seawater, basically created an alkaline setting, euthytic conditions in there that have elevated sulfates, and as a result, diatoms are largely dissolved in these intervals beyond the Thalassiocera sort of pulse that we see at the base. And so when we look at the total diatoms counted, you can see there was almost nothing in there. And what is in those intervals that we see is terpsino, which is basically a marine diatom or a transitional marine diatom found in shallow waters that are very salty on like coastal islands and things like this. And so we know that that interval had to have had elevated alkalinity and elevated salinity from the diatom record alone. And then above this is sort of green intervals where we see complete diatom dissolution, where there were no valves preserved at all. And so again, if we're looking at the pH change, it's suggesting that there's a change in the pH where diatoms are no longer preserved, where they were present in the past and they're not there now. And then suddenly around 4,000 years ago, we see these pulses of planktic species being dominated by Algae in the lake system, a major change back to sort of freshwater conditions. And then again, another around 2,000 years ago, another probably pulse of seawater creating alkaline conditions. And then dissolving diatoms again, and then the very top part of the record, basically we come back to seeing normal sort of freshwater, mostly freshwater diatoms with some pulses of changes towards the top, where there's a little bit more diversity, a little more nutrients in the system, which I interpret to be probably associated with people moving into the environment. So if we look at the other types of organisms that were analyzed from Lake Isabel, Martha looked at the Cladocera stratigraphy of core 5. You can see that the Cladocera follow a similar pattern. The green intervals that are up here, basically Cladocera are missing. These are freshwater Cladocera that are living in the lake, so they're absent during periods like the marine inundation period. And the second marine pulse, basically a reduction in Cladocera, suggesting we have brackish conditions during these intervals where we have green bands transitioning back into normal lake conditions. So it's not just the diatoms that are showing us that story. It's also things like Cladocera. These are some examples of testate amoeba. So the upper parts of the water produce a bunch of testate amoebas. Very rarely in the very lower part of the record, back when it was basically a wetland, we had some testate amoeba. And then ostracods are pretty rare when we find them. Freshwater ostracods occur in the upper part of the record. And also this ammonia is actually a marine foram. So we found some marine forams basically present around this pulse where we think is marine inundation. So these all basically point in the same direction. They match what we expect from the chemistry of the system. And when we reconstruct the history of Lake Isabel, this is basically the pattern that we observed from core 5. So at the base, lake level was low. Lake level rose suddenly. There was a transition to increased salinity and decrease in freshwater diatoms. They became then brackish and dominated by high alkaline conditions, as opposed to the sort of early acidophilic diatoms that we saw. And then a transition to no diatoms at all during this sort of brackish period, second pulse of seawater again coming in up here around 2,000 years ago, and then all of these indicators basically pointing to the same kind of story. So a nice coherent story for what we think is going on from core 5. It's one instance from the lake. It's analyzed at relatively low resolution. So we are aiming to go back and explore these in more detail. Part of the reason we care so much about what's going on in Lake Isabel is because Lake Isabel is a sentinel type of system. It's close to sea level. And when we see rapid change in sea level as we move forward in time into the modern world, where we're worried about global climate change and sea level rise, there are a bunch of very sensitive ecosystems, and Lake Isabel acts as a model for these very sensitive ecosystems. So if we look at the projections for what's going to happen to sea level, a rise in at least 1 meter is expected, probably in the range of 2 to 3 meters as we go forward into the future. And so what this means for these freshwater systems is that they face a sort of crisis going forward, especially those that are very close to sea level that can be inundated by marine waters. When we look at how long it took this system to basically recover from one of these pulses of seawater, in the early pulse, it was thousands of years where the lake basically did not recover. We saw it across all the organisms that were present in that system, a massive change in the biodiversity of the system. And so for us, this is actually really important to think about all of the areas that are vulnerable to flooding from marine inundation today, and using this as a model system for thinking about the influence of global climate change. Okay, so this is the work that we've done in the past. We got a grant funded 2 years ago to look at these systems in more detail. So all of this work that we did was basically done on small grants that we managed to put together. But this is an NSF funded project that we're working on now. Jonathan and some of my students and some of his students and a bunch of our other colleagues went out the spring before last and collected a ton of cores from the lake, a bunch of short cores basically all around. Those are the blue dots that are up there, and then the ones that have red numbers are cored sites where we actually have long cores that go back at least through the Holocene. And what we're aiming to do is look at this transition that we see associated with these marine inundation events, or what we interpret to be marine inundation events. And we want to see, is it present in El Golfete? How far into Lake Isabel is this? And also how much diversity changes through these systems. So we're looking at basically trying to confirm what we think is the storyline for Lake Isabel. And all of these cores that we collected will be analyzed by a bunch of different tools, not just diatoms, but we're also looking at ancient DNA. My colleague Tricia Spanbauer is doing that. And then some biomarkers. My colleague Melissa Burke will be looking at those. And then Jonathan's looking at the sedimentology. And Justin, who's here in the channel, Justin Harden, is going to be the diatom analyst that works with me on analyzing a bunch of the diatom records from the Lake Isabel system and El Golfete systems, looking at how each one of these sort of parts of the lake sort of respond to these marine inundation events and what kind of impact it's having on those systems. Okay, so that's the current plan going forward. We managed to basically collect these cores and subsample them. We haven't started analyzing any of this material yet, so this is all in the future work for the project. But I wanted to talk a little bit about one other part of this project while I still can, before we close, and that is that this is an area that Guatemala in particular that's subjected to a bunch of earthquake and tectonic activity. Lake Isabel itself is a pull-apart basin where we have transform faults or shearing faults that basically are pulling apart to form the lake. And one of the reasons that we're interested in it as well is that we think that there's about 10 million years of sediment going back down to the very bottom of Lake Isabel. We think its history is much, much longer than 10,000 years, but we don't have the right coring equipment or funding to actually analyze or collect those cores yet. But it's in the works, hopefully. And then one of the things that we're exploring is also the effect of the seismicity on the lake system itself. And so you can see here, it's an earthquake-prone region, the Caribbean Sea, the North American Plate, and the Caribbean Plate basically sliding past each other. These red dots are zones where we've had large earthquakes greater than magnitude 7 since 1816. So, just a 200-year record, we've had these major earthquake events that we've recorded, including this one. This is the Pulachic earthquake from 1816 that's in the Guatemala region. And if we look more closely, very catastrophic earthquake that killed something like 26,000 people in Guatemala in 1976. The Algae earthquake had a significant influence on the people in that environment, but also you can see that it it hit all of these lake systems that were nearby to this fault system, including Lake Isabel, but also Lechua, Chicho, Atitlan, and Ayarza. And when Jonathan went out with his crew to collect stuff from Izabal on a different NSF project, they also collected cores from all of these lake systems that we're interested in. These are many of the natural lake systems in Guatemala that have never been studied, or have never been studied for diatoms at least. And so we're interested in what's going on with them. One of the things that Jonathan has been able to find from a geology paper that's soon to come out, where they're talking about the earthquake processes that are going on, is that the earthquake events themselves are captured in each of these, or many of these lake systems. And so these gray bands up here are examples where they find sediment pulses that we believe are material that has been deposited as a result of shaking from the earthquake, causing sediments to come into the lake system. And we're capturing these earthquake deposits across a range of cores. And this is Atitlan, this is Lake Ayarza, this is Chicho, this is Lechua, and this is Ematitlan. And in each of these, basically, they were able to find these thick deposits. They dated these cores to the 1976 earthquake during those intervals. So we know that that basically is associated with it. In some cases, they're massive deposits. In some cases, they're just little tiny pieces of it. Depends on sort of the slope of the lake basin and where the cores were located within the lake. But we see that record continuously through all of these systems. And because Lake Isabel's in that particular system, we're also looking to see if there's any kind of earthquake deposits that we could find associated with the 1976 earthquake from Lake Isabel. But I wanted to just briefly show you some stuff. This is our current work, or Jonathan's current work, where they're publishing on the earthquake records. This is a series of cores that were collected from Lake Atitlan from 2 springs ago when they were out. And you can see these massive deposits associated with what we believe are earthquake deposits spanning across the entire lake system, sometimes massive, depending on where they are in the basin. This is all of the same earthquake deposits from a slightly smaller effect here in Lake Ayarza, but all again at the same time interval in the 1976 range. And what's interesting about this is, of course, these were all short cores that were collected from these systems, but Jonathan has gone back and collected longer cores from all of these lakes as well. And in the longer records, we can basically then use these earthquake deposits as a model for tracking earthquake history in all of these lake systems. In recent years, we took some of these short cores that were collected and analyzed them for the diatom records. So my recently graduated master's student, Christopher Winningham, has been analyzing the records from Lake Amatitlan and Lake Ayarza for diatoms. And this orange interval that's here is actually the earthquake interval. And you can see that it had a very large effect on the types of diatoms that we see. There's the diatoms from before the earthquake, and then basically a major transition. We see much more Ulnaria acus and Algae granulata associated with the post-earthquake deposition. We think this is because the earthquakes basically, when it shakes, carries a bunch of sediments into the lake system. It also carries a bunch of nutrients into the lake system. And so what we see is eutrophication events associated with tectonic activity. And so this record is kind of interesting. You can also see probably some influences of people in the basin. Here's another record shown from Lake Ayarza. Again, the oranges are earthquake interval. We can see early part of the records dominated by Cyclotella, sort of low nutrient or moderate nutrient species, and then earthquake event, and then basically a major transition where we get a bunch of Algae sort of dominating the plankton of these lake systems. Again, probably associated with these major introduction of nutrients into the system. When we looked at Lake Isabel to try to see if we could find some of these earthquake deposits, but we really couldn't. So despite the fact that all of the lakes in the surrounding basin have some influence from earthquake deposits where we can actually see our response. We haven't really been able to identify this sort of thing from Lake Isabel, and we think it might have something to do with the directionality of the earthquake activity. So because we essentially have a series of lakes that go all the way around the margin of the fault, the ones that are basically on the western edge of this, where the direction of the fault was highest, basically got the most shaking. And we think maybe even though Lake Isabel is fairly close to where that fault is, it didn't experience as much of the directionality of those earthquakes. So it's kind of a neat way of looking at it, but also we're exploring how the diatoms are basically affected by it. And again, we can use these very long records that we've collected from all of these lakes to reconstruct past earthquake events prior to the 1976 one, if we can basically use it as a model for what we've observed. Okay, so I think I actually just perfectly hit 45 minutes. I want to thank everybody for listening to my talk. This is just a quote from Charles Darwin: few objects are more beautiful than the minute silicious cases of the Diatomaceae. Were these created that they might be examined and admired under higher powers of the microscope? It's a question that he asked. This is from Origin of the Species. So even in the early days, our scientists were transfixed by the beauty of diatoms. And I think that still continues today. They're very charismatic. And my colleagues, mostly Jonathan Oberst and I, have been working on this together with a bunch of other people. He's at Missouri S&T. NSF, I'd like to thank for their funding. We work very closely with this Continental Scientific Drilling Group at the University of Minnesota. I want to thank all of you for your attention.